As of this morning, May 10, 2026, a sunspot region that already fired 2x2, 5-class solar flares, the strongest eruptions recorded in 78 days, has completed a full rotation around the far side of the Sun and is now crossing back into direct Earth-facing alignment, redesignated by solar monitors as R4436. And the instruments watching it from NASA's Solar Dynamics Observatory are showing a magnetic structure that appears larger in extent than every other active region currently visible on the solar disk combined. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources: USGS, NOAA, the Smithsonian Global Volcanism Program, NASA, and peer-reviewed research. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed, the data is public, the responsibility to check belongs to all of us, but that is not even the complete picture, because what you are about to understand is not simply that a solar storm is heading toward Earth this week. What you are about to understand is that a region of the Sun that has already proven it can shut down radio communications across an entire ocean is returning for a second act, and this time it will be facing Earth directly. The difference between a solar flare that disrupts one side of the planet and a solar flare that disrupts your side of the planet is not measured in technology. It is measured in geometry, and as of this morning, the geometry has shifted. R4436, the designation now assigned to what was formerly known as R4419, is not a newcomer to these instruments. Solar physicists and amateur solar observers have been tracking this region since late April, when it announced itself to the world with a performance that forced pilots in the Pacific and sailors navigating East Asian shipping lanes to reach for their backup systems and sit with static where there should have been voices. On April 23, 2026, at 9:07 p.m. Eastern Time, the Sun released an X2 for class flare from this region. 7 hours later, at 4:13 a.m. on April 24th, it released an X2, 5-class flare from the same source, 2X-class eruptions in 7 hours. The radiation from both events traveled from the surface of the Sun to the surface of the Earth in approximately 8 minutes and 20 seconds, moving, as all electromagnetic radiation does, at the speed of light. There was no warning window. There was no preparation interval. By the time NOAA's Space Weather Prediction Center confirmed the classification, the radio silence had already begun. Solar physicist Dr. Ryan French described those April events as the most intense solar activity recorded in 78 days. He posted in real time as the ionosphere expanded and halted the propagation of radio waves across the sunlit hemisphere. That phrase, halted the propagation of radio waves, deserves to be held at arm's length and examined, because it is choosing its language carefully, and that careful language is itself the warning. What it means, in the terms any navigator, any long-haul pilot, or any maritime operations officer would recognize, is that the high-frequency radio bands that connect aircraft crossing the Pacific to air traffic control simply went quiet. The radio worked. The operators knew how to use it, but the signal had nowhere to go. The ionosphere, the invisible atmospheric layer that ordinarily reflects short-wave signals around the curve of the Earth, had been ionized so severely by solar X-ray and ultraviolet radiation that it absorbed those signals instead of reflecting them. Gone. 4. Periods extending up to an hour, according to reporting from NOAA's monitoring data. Pilots crossing the Pacific Ocean were without long-range voice communication. Satellite backup systems partially compensated. But the word partially is doing considerable weight-bearing work in that sentence. And here is where this account becomes genuinely significant, because the flares of April 23 and 24 were produced by R4419 when that sunspot region was located near the western limb of the Sun, the edge, the periphery, facing partially away from Earth. The coronal mass ejections that accompanied those eruptions were directed outward and away into the interplanetary void rather than toward this planet. The radio blackouts happened because flare radiation, unlike the slower-moving plasma of a coronal mass ejection, travels at the speed of light and cannot be redirected by position. But the geomagnetic storm component, the component that stresses power grids, induces currents in high-voltage transformers, disrupts satellite orbits, and can in extreme cases cause cascading electrical failures across entire continental grids, that component largely missed Earth in April, because the region was not facing us. Now it is facing us. As of the morning of May 9th, solar observers using imagery from NASA's Solar Dynamics Observatory first detected what they described as a returning powerhouse beginning to appear over the Sun's northeast limb, the edge through which active regions emerge as the Sun's rotation carries them back toward the Earth-facing side. Patricio, an observer in Santiago, Chile, who had been photographing the solar disk on May 8th, noted in his observing log that the new region appearing at the 10 o'clock position of the solar limb was expected to be the returning R4419, and that if confirmed, it would have completed a full solar rotation, a rare feat for a region of its complexity. That confirmation arrived on May 9th, when Earthsky reported that the sunspot now peeking over the northeast solar horizon appeared larger in extent than all other active regions currently visible on the solar disk. The Solar Ham Monitoring Network, which provides continuous analysis for radio operators and space weather professionals, confirmed on May 10th that the region has been redesignated R4436, that it continues to rotate into Earth-facing view, and that it has already demonstrated ongoing activity firing an M26 class flare from the far side on May 7th at 1514 UTC. That M-class flare was almost certainly stronger than the measured classification because the source region was still located behind the solar limb at the time, and the sun's own horizon partially obscured the true intensity of the eruption from Earth-based sensors. To understand what is accumulating in that region, it helps to understand what an X-class solar flare actually is. The solar flare classification system uses letters A, B, C, M, and X, where each ascending letter represents roughly a tenfold increase in peak X-ray flux measured at Earth's orbit, and X2. 5 flare, the category produced twice by this same region in late April, does not fit neatly into everyday frames of reference. But consider it this way: the electromagnetic energy released in a single X-class solar flare exceeds the total global energy consumption of every human being on this planet over approximately 10,000 years. That energy is not released in years or in days, it is released in minutes. It is released in a burst so intense that it expands the Earth's upper atmosphere, heating it, thickening it, causing satellites in low Earth orbit to experience drag where there was virtually none before. The energy arrives here before any instrument on the surface can warn the instruments that depend on warning. The question is not whether our 4436 will produce flares as it crosses the Earth-facing disk. The question is what classification those flares will carry and whether the associated coronal mass ejections will be directed at us. The Met Office Space Weather Center, whose forecasters have been monitoring the situation, noted on May 9th that a faint coronal mass ejection from May 6th carried a chance of delivering a glancing blow to Earth on or around May 10th. The language used was a slight chance of active to G1 minor storm intervals, a G1 storm. On the NOAA geomagnetic scale, the lowest tier of named geomagnetic disturbance is not the kind of event that makes news in most circumstances. But it is instructive here as a baseline because what the Met Office was describing was a glancing blow from a faint CME produced before our 4436 had fully rotated into Earth-facing position. The geometry is now changing. The region is rotating in. What it fires this week, it fires at us. To understand what at us means, it is necessary to travel backward to a morning in March 1989. The date was March 13th. The location was the province of Quebec, Canada, at 2:44 a.m. local time, without warning that would have reached the average household. The hydro power grid collapsed. It did not fail in the way that grids fail during a thunderstorm, where a transformer overloads and a neighborhood goes dark. It failed in the way that a geomagnetic storm forces a grid to fail wholesale, cascading, simultaneous. Within 90 seconds of the initial cascade beginning, the entire province of Quebec was without electrical power. 6 million people, not a neighborhood, a province. They remained without power for 9 hours. The storm that caused this collapse was classified as a G5, the maximum on NOAA's geomagnetic scale. It produced geomagnetically induced currents, electrical currents driven by the sun's interaction with the Earth's magnetic field, flowing through the ground itself and up into any conducting infrastructure connected to that ground: power lines, pipelines, telegraph cables. The Quebec grid was simply not designed to survive a current arriving from beneath it. Almost no grid built in the 20th century was. This is not a hypothesis. This is documented in the geological record and in the engineering record and in the maintenance logs of every large transformer that survived that night, some of which required days of repair before they could return to service. The March 1989 event was not even the largest storm on record. It was not close to the largest. The Carrington event of September 1859, named for British astronomer Richard Carrington, who observed the solar flare preceding it, produced a geomagnetic disturbance so intense that telegraph operators across Europe and North America reported sparks jumping from their equipment, fires igniting in telegraph offices, and in some documented cases, the ability to operate telegraph lines without any battery power at all, using the geomagnetically induced current flowing through the wires as the sole source of electricity. Auroras were visible in the Caribbean. The equatorial or loval, which in a quiet period sits far above the polar regions, descended to latitudes where auroras had never been observed by living memory. A USGS analysis of a Carrington scale event applied to contemporary infrastructure estimates that between 20 and 40 million Americans would lose electrical power. Lloyd's of London, in their own assessment, placed the global economic cost of such an event at $1 trillion, approximately 1.4% of global GDP destroyed in a single geomagnetic interaction. High-voltage transformers, the enormous and bespoke pieces of infrastructure on which continental power grids depend, take an average of 4 years to manufacture. A Carrington-class storm arriving during a period of peak solar activity, a period that, according to NASA and NOAA confirmation issued in late 2024, the Sun entered with solar cycle 25 and has not yet fully exited, would destroy hundreds of those transformers simultaneously, and the queue to replace them does not exist. It would have to be created from nothing, in a world where the manufacturing infrastructure for those transformers is itself dependent on the grid they would be replacing. This is not speculation. This is a scenario that has been formally modeled by USGS, by the Federal Emergency Management Agency, by Lloyd's of London, and by Defense Research institutions on multiple continents, the monitoring is in place and detection is possible, but prediction is not. And the region now rotating into Earth-facing alignment is the same region that demonstrated twice in a single week that it is capable of X-class behavior. Consider the city of Anchorage, Alaska, population approximately 291,000 people. It's at a geomagnetic latitude that places it squarely within the high-risk zone for geomagnetically induced currents during even moderate-level geomagnetic storms. In the winter, temperatures in Anchorage can fall below -20 degrees Celsius, cold enough that a 9-hour power outage of the kind Quebec experienced in 1989 becomes something more than an inconvenience. Consider also the shipping lanes of the North Pacific, where commercial aviation routes cross thousands of miles of open ocean with no terrestrial radar coverage and no communication infrastructure other than the high-frequency radio bands that are 419 already silenced once in April. The pilots making those crossings on any given day are professionals with training and procedures for exactly this scenario, but procedures exist precisely because the scenario is real. Ask any long-haul Pacific aviator whether they have ever had to switch to backup navigation following a radio blackout event, and the answer will not be hypothetical. The solar wind, it must be understood, is not an occasional phenomenon. It is constant. The sun does not periodically emit a stream of charged particles into the solar system and then rest. It emits continuously a perpetual outward flow of protons, electrons, and alpha particles that fills the space between the sun and every planet in this system at all times. What changes during a solar flare or a coronal mass ejection is not the presence of that wind, but its character, its density, its speed, its embedded magnetic field orientation. The critical variable, the one that determines whether a CME directed at Earth produces nothing more than enhanced auroral activity or produces a geomagnetic storm capable of stressing continental power infrastructure, is the direction of the B's component of the interplanetary magnetic field. When B's points northward, it is oriented in the same direction as the Earth's own magnetic field, and the two largely repel each other. When B's turn southward, when the solar magnetic field and the Earth's magnetic field are oriented in opposition, a process called magnetic reconnection occurs at the dayside magnetopause. The sun's energy pours into the magnetosphere, the auroral oval expands, currents begin to flow in the ionosphere and in the ground beneath your feet. The Met Office Space Weather Report for May 9th noted that the B's component had been measured pointing strongly southward at the time of writing, a condition that, in the presence of elevated solar wind speed from an approaching coronal interaction region, produced a G2 geomagnetic storm on May 8th that NOAA's own forecasters had not anticipated. The agency issued a statement acknowledging that the storm had been stronger than expected and that the cause remained unclear. A G2 storm arriving without adequate forecast warning, during a week when a major returning active region is crossing into Earth-facing alignment, while the background solar wind remains elevated from a preceding coronal hole, that is not an alarming sentence. It is a description of current measured conditions. Solar Cycle 25, the ongoing 11-year rhythm of solar magnetic activity that governs how frequently and how intensely the sun produces flares, coronal mass ejections, and sustained geomagnetic storm activity, entered its solar maximum phase, confirmed by NASA and NOAA in late 2024. Solar maximum does not mean a single peak day of activity followed by decline. It means an extended period of elevated activity, a plateau of heightened danger that can persist for months or years. We are in that plateau now. The radio flux of the sun, measured by ground stations monitoring the 7 centimeter wavelength and used as a proxy for overall solar activity, stood at 120 solar flux units as of May 9, 2026, according to SpaceWeather.com. This is a meaningfully elevated reading, consistent with an active sun in its maximum phase, and consistent with a solar disk that contains a region now redesignated R4436 that has already proven capable of producing the strongest flares in 78 days. The Thermosphere Climate Index, which measures the energy deposited into the upper atmosphere by solar extreme ultraviolet radiation, registered 1687 times 10 to the 10th watts as of May 9th. For context, the historical maximum recorded for this index measured during the intense solar activity of October 1957. Another period of exceptional solar maximum was 49, 4 times 10 to the 10th watts. The current reading is elevated but not extreme. What matters about that number is not where it stands today. What matters is where it could stand by the end of this week, if our 4436 produces the kind of output it demonstrated in late April, and if the associated plasma is directed toward Earth rather than away from it. Now consider what lives inside the radio frequencies that this region has already demonstrated it can silence. Consider a fisherman working the waters of the Bering Sea aboard a vessel that communicates with harbor authorities and other ships via high-frequency shortwave radio. Consider a bush pilot flying instrument-only approaches into a small Alaskan community during marginal weather, relying on GPS signals whose accuracy degrades during periods of ionospheric disturbance. Consider the operators of emergency medical services in rural regions where cellular coverage does not exist and high-frequency radio is not a backup. It is the only communication infrastructure in place. An R3 class radio blackout, the classification assigned to the April 23rd and April 24th events, disrupts weak and minor High-frequency communication as standard, and at its R3 classification produces wide-area blackout of HF radio communication with loss of radio contact for about an hour on sunlit side of Earth, according to NOAA's own scale descriptions, an hour. On the sunlit side of Earth, not on the dark side, on the side currently facing the Sun, the side that is also facing our 4436 as it crosses into Earth-facing alignment this week, the system is not inactive. It is accumulating. What the scientific community chooses to say carefully in this context is that elevated M-class and X-class flare probability exists while our 4436 transits the Earth-facing solar disk. The solar ham monitoring network used by radio operators who depend on this information professionally characterize the situation as presenting an ongoing chance for moderate M-class activity, with the precise behavior of the region requiring further observation as it rotates into full view. This is the language of professionals who have learned through experience that our 4419 now our 4436 does not announce its decisions in advance. It announced them in April with 8 minutes of warning. 8 minutes is the travel time of light from the Sun to Earth. It is, in every meaningful sense, no warning at all. The connection between solar activity and Earth's broader systems extends further than the conversation about radio blackouts and power grids normally allows. Geomagnetically induced currents, the ground-level electrical currents produced when solar storms reshape Earth's magnetic field, flow through more than just power lines. They flow through oil and gas pipelines. They flow through underwater cable infrastructure. The Trans-Alaska Pipeline, which carries approximately 500,000 barrels of crude oil per day southward from Prudhoe Bay, has monitoring systems in place specifically to manage the corrosion accelerated by geomagnetically induced currents during geomagnetic storm periods. This is standard operating procedure. It is not theoretical. It is managed routinely as a known and documented consequence of living on a planet with a magnetic field that the Sun periodically disturbs. Meanwhile, at higher altitudes, the satellites on which the global navigation system depends are experiencing increased atmospheric drag during elevated solar activity, because the thermosphere, the outermost layer of the atmosphere, expands when solar extreme ultraviolet radiation heats it, and expanded atmosphere means more resistance. And more resistance means orbital decay, and orbital decay means every satellite operator in low Earth orbit must continuously recalculate and adjust their orbit to avoid drifting into re-entry trajectories. This is happening right now. The thermosphere is in an elevated state. The satellites are adjusting. The adjustment is routine until the storm is large enough that the required corrections exceed what the onboard propulsion systems can provide on the timescale required. And ocean temperature anomalies, the persistent warming of the upper layers of Earth's oceans documented by NOAA buoy networks and satellite altimetry, are connected to this solar story not through a direct physical pathway but through the broader logic of a planet in which all surface systems are driven ultimately by the same energy source. The Sun is not simply a provider of visible light. It is the energy budget of an entire planetary system. When its output varies, when solar extreme ultraviolet radiation increases during solar maximum and heats the upper atmosphere, when energetic particle events alter the chemistry of the stratosphere, those changes do not remain isolated in the upper atmosphere. They propagate downward through coupled atmospheric systems whose full behavior scientists are still mapping. The question is not whether the Sun influences Earth's coupled systems. The data confirms it does. The question is the precise mechanism and the precise scale, and honest science in 2026 will tell you that the mechanism is understood in outline and the scale is still being measured. This morning, May 10, 2026, Earth's magnetic field is registering quiet to unsettled conditions, with a KP index sitting around level 2 according to real-time data from NOAA's Space Weather Prediction Center. The fast solar wind effects that drove the unexpected G2 storm on May 8 are fading. The current conditions, as the most recent 3-day forecast issued at 12:30 UTC this morning confirms, do not project G1 or greater geomagnetic storms through May 12th. The maximum expected KP for the forecast period is 2. This is a quiet forecast, but the forecast was issued before our 4436 has fully rotated into view, before the instruments that measure the full complexity of its magnetic field configuration can see it completely. Before it has had an opportunity to demonstrate what it intends to do during its second transit of the Earth-facing disk, the system is quiet right now. The system was quiet on April 22nd, the day before our 4419 produced 2 X-class flares in 7 hours. The instruments are watching. NOAA's GOES-19 satellite, which carries the SUVI instrument providing continuous extreme ultraviolet imaging of the solar corona, is watching. NASA's Solar Dynamics Observatory is watching. The Deep Space Climate Observatory, stationed at the L1 Lagrange point approximately 1.5 million kilometers sunward of Earth, is watching, and it will be the first instrument to detect any incoming coronal mass ejection associated with new flare activity. When a CME arrives at Discover's position, the warning time it provides to Earth's surface is approximately 15 to 60 minutes, depending on the CME's speed. For the fastest observed CME's events that have reached Earth in as little as 18 hours from the time of the originating flare, that warning is the entire window available to grid operators, satellite controllers, and aviation authorities to implement protective action. In practice, this means switching high-voltage equipment into protective modes, adjusting satellite orientations, and rerouting flights away from polar routes where communication disruption is most severe. The question is not whether the monitoring is sufficient. The monitoring represents the most sophisticated space weather surveillance network ever assembled by human civilization. The question is whether the infrastructure being protected by that monitoring is resilient enough to survive what the sun is capable of producing and what the verified historical record confirms it has produced before. The answer, according to USGS, according to Lloyd's of London, according to the Federal Emergency Management Agency's own scenario planning documents, is no, the infrastructure is not fully resilient. A Carrington-class event arriving today would exceed the protective capacity of the systems currently in place. Between 20 and 40 million Americans would lose power. Global economic damage would exceed $9 trillion. Blackouts could last from 16 days to 2 years. And the sun that produced the Carrington event of 1859 is the same sun whose active region R4436 is crossing into Earth-facing alignment this morning. The record of what the sun has done is preserved in ice cores drilled from the Antarctic and Greenland ice sheets, where cosmogenic isotopes beryllium-10 and chlorine-36 produced when energetic solar particles interact with atmospheric nitrogen and oxygen are laid down in measurable concentrations that allow scientists to reconstruct the history of solar particle events extending thousands of years into the past. That record contains evidence of events far larger than the Carrington event. The Miyake event of 775 AD, first identified in tree-ring carbon-14 records by Japanese researcher Fusa Miyake in 2012, produced a spike in cosmogenic isotopes approximately 10 times larger than anything observed in the modern instrumental record. Its cause remains scientifically debated, but the magnitude of the solar particle event required to produce that signal exceeds every event for which we have direct instrumental measurement. Whatever happened in the year 775 dwarfed 1859, and 1859 dwarfed March 1989, and March 1989 produced 9 hours of darkness across an entire Canadian province. The scale descends from the historical into the contemporary in a straight and documentable line. And somewhere on that line, somewhere between the R1 minor radio blackout conditions that NOAA's systems have been measuring this week and the far end of what this active region has already proven it can produce, is the event that will occur over the next several days as R4436 faces this planet directly. Not certainly. Not inevitably. Probability forecasting in solar physics is precise in its methods and honest in its limitations. But the instruments that have already watched this region fire 2 X-class flares in 7 hours are watching it again now, and the instruments that failed to anticipate a G2 storm from a faint CME earlier this week are calibrating their models accordingly. The radio operators in high-latitude communities, the aviation dispatch centers routing polar flights, the grid operators in Quebec who rebuilt their systems after 1989 and installed ground fault protection that they hope that they have verified will perform better this time, the submarine cable maintenance teams monitoring the Atlantic and Pacific fiber routes, all of them are watching the same thing, the solar dynamics. Observatory is watching the same northeast solar limb, the same returning region. The same magnetic field complexity that was classified beta-gamma in April and has not yet been fully characterized in its current configuration. The sun does not negotiate, it does not issue schedules. It accumulates stress in its magnetic field lines over days and weeks, and then it resolves that stress in events that last minutes and send their consequences across 150 million kilometers of space to arrive at a planet that has built its entire technological civilization on the assumption that the electromagnetic environment will remain stable. That assumption has been tested before. It has failed before. The failure is in the geological record and the engineering record and the insurance actuarial record. It will be tested again. The monitoring is in place. The detection is possible. Prediction precise, actionable, minutes 2 hours in advance prediction of exactly when the next X-class flare will fire and exactly where the associated CME will be directed remains beyond the current reach of the most advanced space weather forecasting system ever built. What the official data actually shows is that a region of the sun with documented X-class behavior is crossing into direct Earth-facing alignment on the morning of May 10, 2026, while the background solar wind remains elevated, while the B's component of the interplanetary magnetic field has already demonstrated this week its readiness to turn southward without adequate forecast warning, and while the Earth's magnetosphere is recovering from a G2 storm that no forecast had predicted. The system is not inactive, the system is accumulating, and the sunspot that already silenced the Pacific once is facing us now, and it has not yet spoken.